All right, so I hope by now you understand that where we're headed with all of this stuff is this idea we've got this wave function, and the square of that wave function gives you some probabilities. And the reason we have these waves is because Schrodinger's thinking, well, actually it looks like electrons can behave as waves. I just want to reiterate this whole thing about standing waves. Now I'm going to use I know electrons obviously you'd conceptualize as being in a three-dimensional space, but if we just go back to basically a linear dimension here, and we're looking at standing waves, here's an example where we've got a string attached with two flanking points here. Let me just get this pen with two flanking points. No, that's my laser pointer. Where's my pen? There it is, two flanking points there and there. And as I said before, it's basically the case what you're trying to do when you make a standing wave is you flick a wave and keep flicking it at the right frequency, and as it bounces back, then you get at the right frequency this standing wave. Now, bottom line is when you do that with a linear system like this, you can very easily represent it. So here's a case where we've got our first frequency, but then if you do it again and you get the right frequency again, you get a second frequency where you get standing waves, and then you get a third, and then you get a fourth. Now that the important point to all of this is that these frequencies are quantized, and if you like, their energies are quantized. There's one, there's two. It's not 1.5, it's 2. Then it's 3, and then it's 4. Okay, so that's the important point. I just want you to keep that in mind, and that's why I've got here fixed point boundaries for waves generate integer values forming standing waves. That is, their quantized values. There's another standing wave demonstration there for you if you want to click on that and just make sure you understand what a standing wave is. Okay, now, experimental evidence that electrons actually do indeed behave as waves. Well, this is the classic double slit experiment with electrons. In fact, this experiment is showing that electrons behave as waves and particles at the same time, which is crazy but true. And in fact, in this experiment, and let me just walk you through this, here we've got our electron source, so electrons are traveling in this direction, and we've got our two slits here. Now, as before, if you want to try, we're going to eventually try and make a diffraction pattern over here, but as before, if you want that diffraction pattern, obviously the slits have to be small enough that they correspond more or less to the wavelength of the waves in question. So this takes a setup with very small slits here. Now the other crucial point here is that you only set it up so that this electron source is basically only ever emitting one electron at a time, and that's an important point as well, right? You can actually set it up so it emits more than one electron at a time. This is one electron at a time. Okay, so what do you see? Well, as initially, so this is as time goes on, you eventually get this diffraction pattern here. Initially, what you see is each one comes through, it just goes through one of the slits, one or the other, and obviously you then end up with a spot. So each little spot here represents an electron, but over time, if you let those spots build up, you end up with a diffraction pattern. The diffraction pattern's indicating these electrons are behaving as waves. The spots are actually indicating they're behaving as particles. What? Well, that's what the experiment shows. And you can get as cranky as you like that that's not the way our world works, but in the quantum world, that's the way it works, right? So there is such a thing as things behaving as waves and particles, and electrons being small enough, according to de Broglie's equation, are small enough that they can indeed behave as waves. The really mind-blowing bit, you don't really have to understand this if you don't want to, is that you can't really get a diffraction pattern with waves unless, like this diffraction pattern here, unless you've got two waves going through those two slits. That's when you get your diffraction pattern. But we're only letting one electron at a time go through, right? So it's almost as if, to get that interference pattern or diffraction pattern, each electron is traveling through as a particle, and then at the same time, it's actually going through both slots at the same time, behaving as a wave. Well, who said that things had to behave the way we experience them in everyday life? Clearly these guys don't. A very, very nice experiment that shows all of that. It's this paper here. And if you get a chance, I would really suggest you have a look at it. It's a great, nifty piece of experimental science. Now, there's no point you trying to rationalize things in everyday terms. This is the experiment. Electrons can behave as particles. They can behave as waves. So let's just summarize it again, right? We've got electromagnetic radiation, right, which light is one sort. We've got experimental evidence, very clear experimental evidence, to show that that kind of radiation behaves as waves. It also behaves as particles with the photoelectric effect. Electrons, that previous experiment, you can see they behave like waves and particles. In fact, in that experiment, you can show they're behaving as waves and particles at the same time and passing through two slits at the same time. It's pretty clear electrons are occupying quantized energy levels. And we also know from classic physics that if you take waves and you put boundary restrictions on them, then to get standing waves, they only occur at particular integral frequencies. That is, their energy levels are quantized. Schrodinger's brilliance was that he pulled all of this stuff together here, and then he said, okay, well, I don't know if he really said this, but you can imagine him saying something like this. If we imagine that our electrons, we have electrons behaving as waves in atoms, that is, there's boundaries, and they produce standing waves, they would do so at quantized energy levels. And he did the maths to show that that's the case. Now, before we get on to looking at Schrodinger's quantum numbers and things in a little bit of detail, I just want to again jump back to that standing wave idea. And now we're going to beef it up a little bit, and we're going to look at what you would actually get for standing waves in 2 dimensions. Now, the mathematics behind this is overwhelming, to say the least, and clearly you guys don't have to know any of it, but you can actually show this kind of standing wave phenomenon very easily, just simply doing the experiment. So in 2 dimensions, if I've got a plate here like this, it's a flat plate, obviously that's in 2 dimensions, and if I sprinkle some sand or powder on it like this, and then make it a vibrating plate, and I can change the integral frequencies in that vibrating plate there, I can start to see these standing waves being produced. And of course, they're only going to occur at integral frequencies. Now, as I said, the maths is complicated, and really the only point I'm trying to make here is that you can develop mathematical equations that describe this. And the other point I wanted to make was that the patterns are obviously there. They're predictable, and they're getting much more complicated than what they are for a linear standing wave. As you could see in the linear standing wave, it's either 1 or 2 or 3, and these guys are doing some fairly complicated things here. But you do get these discrete boundaries and shapes. Now, if we go one more dimension, that is 3 dimensions, which is what Schrodinger did, then you can derive the mathematics. In fact, you can show this in things like a sphere anyway, and you can get these patterns, and you can actually produce these patterns like this, right? So these are three-dimensional standing wave patterns. Now, when you first look at this, you go, well, why are they like that? Well, the answer is because of the mathematics. And if you look at these, you can see these get pretty complicated. So it's not surprising that these three-dimensional standing wave patterns get pretty complicated as well. But there they are. Okay, so when Schrodinger developed his equations, he could then, he used obviously standing waves, 3 dimensions, and surprise, surprise, when you do all of that, what you're doing is basically using particular wavelengths for the electrons, and you basically end up with these standing wave patterns from those equations. As I said, the equations are just mind-boggling, but the bottom line is you end up with the same types of patterns. These are in 3 dimensions. Now, the first pattern that you see when you develop these equations, so if you like, that's the equivalent of the first harmonic in a linear standing wave, is this pattern here, which is a sphere. Now, the pattern isn't called a sphere, it's actually called sharp. I'm not actually quite sure why, but it doesn't matter. The next one's called principal, the next one's called diffuse, and the next one's called fundamental. So you could refer to them, the pattern itself, the 3-dimensional pattern, as S, P, D, and F, like that. Okay. Now, before we go any further, let's just look at these patterns a little bit more. So this is a sphere, and then in the next harmonic, if you like, in 3 dimensions, you end up with what look like these kind of sphere-y type things joined together. So this is actually like this, and this is like this, and that's going back into the plane there, right? Back in that direction there, right? So here we've got 1 type, here we've got 3, here we've got 5, here we've got 7, and that kind of makes some sense too, right? That if you're going to get these kind of harmonic progressions in 3 dimensions, there'd be some pattern in things like the numbers of them. So there's 1, there's 3, there's 5, there's 7. Okay, cool. Notice the shapes. In this case, by the way, these guys here, if you kind of put them together to see what they would look like, it would be in 3 dimensions. So there'd be an X, a Y, and a Z dimension with these things poking in each of those 3 dimensions. These ones are a little bit different again and again. They're getting way, way complicated and weird there. Okay, so Schrodinger's next idea was that, okay, these things, each one is called an orbital. Not an orbit, like, you know, the Earth orbiting around the sun kind of thing, but an orbital, where as a consequence of his equations, he figured out that there should be 2 electrons maximum per orbital. So in this S orbital here, you can have 2 electrons. In this P orbital here, you can have 2. In this one, 2. In this one, 2. In this orbital here, 2, 2, 2, etc. Okay, the significance of that will be apparent in a minute. The other thing is, it's not just the shapes, you've got to look at the energies involved. So this is the lowest energy, higher, higher, higher again. And these are discrete energy levels. And so his hypothesis then was that if I've got an electron, let's say I was playing around with sodium and heating it up. So what's happening is I've got an electron that's originally here, I heat it up, it jumps to here, and then when it jumps back, it can only jump back to this level here, which is a discrete amount of energy given by E equals h nu, okay? And that was basically where these things come from. Okay, I'm going to leave it at that, and then I'll get on to the next section.